Let us study the spectral characteristics, the spectral characteristics of multi-rate systems, particularly downsampled and decimated signal using a Matlab program. Let's generate a sequence with 512 samples of a signal x of n, discrete time sequence, which is composed of three sinusoidal sequences. X of n is equal to sine of 2 pi f1n plus 0.9 times of sine of 2 pi f2n plus 0.73 times of sine of 2 pi f3n. So three sequences are ready, three sinusoidal sequences. They are all summed up together to create x of n. Along with this, we plan to generate a sequence S of n, which is of random in nature, RANDN of 1 comma n. We shall sum up the x1 of n or x of n for this matter, right? Let me call this as x1, right? With 0.8 times of S of n, S of n. Okay, mention this asterisk in a better manner. Okay, uh, let's analyze the spectrum of x of omega, spectrum of this signal also, for which we need FFT function. Let's apply this x1 as an input and let's compute, for example, 1024 point FFT to generate the spectrum of the original signal. To view the spectrum, let's define a scale, frequency scale, starting from 0 in steps of 1 by 512, 2 by 512, 3 by 512, 4 by 512, etc. till 512 minus 1 divided by n minus 1 divided by en will be the set of tick marks available on the scale. Let's view the spectrum and we shall downsample it. Let's see the spectrum. Also, we shall work with decimate and see the spectrum. I hope you would have started listening to this spectral characteristics of a downsampled signal, decimated signal, for which we need x of n. We shall generate 512 samples of x of n. X of n, maybe let me call this as x1 of n, where there are three components present. It is composed of three components: sine of 512 f1 or sine of 2 pi f1n plus 0.9 times of sine of 2 pi f2n plus 0.7 times of sine 2 pi f3n. There are three frequencies now. Let me define f1 is equal to 0.01 and f2 is equal to, for example, 0.04 and f3 is equal to, because the range of frequencies, discrete time signals, discrete time sinusoids would be between minus 1 by 2 to plus 1 by 2. So let me choose the third frequency as 0.35. Minus 0.5 to plus 0.5, any number, any value could be given as the frequency of the discrete time sequence. And I just want to remind you one thing. It is sufficient if you generate some 512 samples from the sequence, so that you can define the time axis also as 0 to n minus 1. So capital N is ready, time axis is ready, three frequencies are defined. We shall create x1 of n, which is composed of three different 2 pi f1 of n, 2 pi f1n, 2 pi f2n, 2 pi f3n. There are three sinusoidal signal components, and we shall also work with random sequences. S is equal to RANDN of 1 comma n. So x is equal to x1 plus 0.8 times of s will give you the original signal. Let's apply a Fourier transform on it. Let's generate x. This x is the spectrum. The spectrum can be viewed also. You can plot it and view it. Okay, this is how the signal is ready, right? Let's get into the program part. Let's keep clear all as the first statement and close all as the next statement. And of course, CLC is of course required. Now let's generate the input signal. Let me define the total length of samples is equal to capital N, which is equal to 512, and N is equal to 0 to N minus 1. Yes, the time axis is ready. Let me define those frequencies. F1 is equal to 0.01, F2 is equal to 0.0, for example, 0.4, and F3 is equal to, what is this? This is 0.35, as I have told you already. It's generating sinusoidal signal components of three different frequencies. That was our objective. Okay. Based on this objective, we shall define what is um, x1. For example, x1 is equal to sine of, yes, 2 asterisk pi asterisk f1 asterisk n is the first component, whereas sine of, what is the second component? 0.9 times of sine of 2 pi, 2 asterisk pi asterisk f2 asterisk n. What is the third component? It is 0.7 times of sine of 2 pi f3, yes, n. Okay. Now the signal is generated with three components. So S is equal to, what is S? It's a random signal, RANDN, of dimension. Dimension must be equal to the length of x1. Then only I can add both. So that x is equal to x1 plus S is the signal. Okay. Or you can even go for x1 plus 0.8 times of 0.8 times of S. Okay. Signal is ready. Original signal is ready. To know the spectrum of it, x of x is equal to x of omega, which is obtained using f of t function, f of t of the small x, and I just plan to evaluate frequency spectrum over some 1024 samples, frequency tick marks for each frequency. How to define the frequency scale? F is equal to, starting from 0, 1 by 512, 2 by 512, 3 by 512, 512 minus 1 divided by 512 is the size of our frequency scale. Okay, n is defined, small n is defined, f1, f2, f3, f3 are defined. Three sinusoidal components are individually generated, added together to produce x1. Let's create random noise in the name of s. It is stored. So x1 added with 0.8 times of noise will give me the x, desired x. This x is analyzed in spectral domain using f of t function with the length capital N is equal to 1024 and small f is equal to 0 colon 1 by 512 colon 512 minus 1 divided by 512. So let's plot the spectrum. How will it look like? Say for example, I have subplot of 3 comma 1 comma 1. Okay, plot. How to generate plot? Plot of f comma, f will be taken on the x-axis and f comma abs of x of, okay, x of the spectrum. I just take only the 512 components of it and then I display one part of it. Actually, instead of double side spectrum, we just go for only one side of the spectrum. We shall plot it. Okay, good. What is the x label, what is the y label, that and all you can decide. Now let me downsample it. For downsampling, we shall have the d factor d is equal to 5. Okay, what is y? Y is equal to downsample of small x comma d. Now you can see downsampling factor is 5, and downsampling operation is carried out x comma capital D. Now for this downsampled signal, let me view the spectrum of it using f of t function. F of t of what is the input? The downsampled signal. For how long? What is the length of frequencies over which it is evaluated? 1024 point frequency scale, computing the spectrum of the downsampled scale. So let me have what is the result of this decimation operation. What is the decimation factor? By 5. Let's see how to plot it. Plot of f comma abs of y of 1 colon 512. You can just see this, and you can also notice plot symbol is signal. Plot will give you the spectrum. Plot will give you the spectrum. This part is over. Let's see how to decimate instead of downsample. So let me have a new notation yd, which is equal to decimate of what is this signal x. What is the decimation factor? By a factor of d. By a factor of d. What is capital yd? It is equal to the spectrum. How to view it? F of t of what is small yd comma 1024. How to plot it? Plot of f comma abs of y of or yd of, I take only 512 values of the spectrum to view outside. Let's have this. Good. What is y label? What is legend? What is x label? You can mention it. You will ask me a question, sir. Instead of using the plot command here, let me have subplot. Yes, it is agreed. Subplot of 3 comma 1 comma 3. Let me have a spectrum on a separate part. Very good. You can view the signal. Likewise, let me get into another problem. You try this on Matlab window. Let's study the spectral characteristics, the upsampled and interpolated signals by using Matlab programs. Let's generate 512 samples of the signal. As I told you already, let me have x of n. As I told you already, what is that? Sine of 2 pi 2 pi 0.05 n is the first component. F1 is equal to 0.05, and the second component is zero point 0.9 sine of 2 asterisk pi asterisk 0.09 n, whereas let's even have two. There is no necessity that we have to work with three sinusoidal components. Work with two sinusoidal components. The third component can be 0.8 times of the random noise added to it. Let's X is an additive wide band noise of normal distribution. It can be generated using Matlab function. The Matlab function is RAND. I'll mention what is S of n. S of n can be called as additive wideband noise of normal distribution. Normal distribution. It is generated using RANDN in Matlab. Okay, let's plot the original upsampled signal, interpolated signal. You can work with a number of such things actually. Okay, shall we? The first one is, first of all, we shall create the Matlab program for it. How to work with Matlab? The first command will be CLC. The next one will be close all. The next command will be clear all. Yes, the Matlab command window will not run any of the preceding inputs. Now it will simply work with signal generation with two components. Shall we? Capital N is equal to 512. Okay. Small n is equal to 0 colon n minus 1. Agreed. The next one will be the frequency f1 is equal to 0.05. Yes. And f2 is equal to 0.09. Look at the question. Two frequencies are ready. Prepared? Prepared. Very good. Now we shall see how the composite signal, which comprises of two sinusoidal components, can be generated. X1 is equal to sine of is sine of 2 asterisk pi asterisk, what is it, f1 asterisk n plus zero point 0.9 times of sine of 2 asterisk pi asterisk. Yes, what is f2? F2 is known to you. It is already loaded in the name of a variable. Good. And yes is the additive white or white band noise of generally white band noise, which is generated using Arya-Indian function of normal distribution. Normal distribution, it is readily available. So now I can use Arya-Indian of 1 comma n. Yes, the noise is also ready. Additive white Gaussian noise, and you can see x will be equal to the sum of x1 and s. Yes, sometimes the s need not be taken as such. It can be even scaled down by 0 0.8, 0 0.7, 0 0.4, so that the signal will be of a clearly represented signal. So capital X, what is capital X? Capital X is equal to, let's analyze the spectrum. How to analyze it? Take the signal and apply 1024 point f of t. Good. Let me define the frequency scale for discrete time sequence 0 colon 1 by 512 colon 512 minus 1 divided by 512. So you can notice that the 512 signal is ready. Good. If I use a subplot of 3 comma 1 comma 1, and if I make use of the function called plot of f comma abs of, say for example, capital X of 1 colon 512, I just take only the first 512 samples alone and we shall represent it as a graph. Okay, let me now define an interpolation factor of 5. Right, I is equal to 5, upsampling factor. Let me have simple upsampling using the function upsample. What is the input? X is the input. What is the interpolation upsampling factor? I. So you can notice that capital Y is equal to the spectrum which is applied on the output signal Y comma 1024. Right. All right. For this upsampled signal, if you ask me to plot the spectrum, so then I can go for a subplot of, say what is the subplot? 3 comma 1 comma 1 has been already used. So 3 comma 1 comma 2, which is going to have the plot. What is the plot? The plot has f as the scale. Very good. F as the scale, comma. Obviously, I need to modulus of y of 1 colon 512 is the spectrum with which I can see the output. Upsampling factor. See, now I just want to introduce one more function related with upsampling. What is it? I'll just go for yi upsampled, or y, yi or y1, whatever it may be. Let me have the function called interp. What is it? It is interp of the input signal and the capital M. That will help me to find out the spectrum of it. How to apply spectrum? Take Fourier transform and keep y1 as an input, and the other factor is the upsampling factor, which is 1024, for example. Sorry, frequency scale, maximum number of tip marks over the frequency scale. Computing the spectrum of the interpolated signal, interpolated by D, is a signal. Okay, how to see the result? So I can just go for plot of subplot of, yes, 3 comma 1 comma 3, and you can notice the plot will be of f comma modulus of, what is it, modulus of, yeah, yi of 1 colon 512. 1 2 3 4. Yes. So upsampling and downsampling both have been seen now. Did you know one thing? In our graph so far, we have generated only the spectrum. If you want to seriously view, let me have another figure, time domain analysis using graphical windows. Subplot of 3, 1, 1. Yes, stem of 0 colon 31. Yes, we take only 31 sample, 1 colon 32. Here we may have to work again. The signal, original signal, we have taken only 32 samples. Let's go for subplot of 3, 1, 2. Yes, fantastic. What is it? Stem of, yeah, stem of starting from m minus 1 colon m multiplied by 32 minus 1. Let me take only those samples. How to view it? M minus 1 colon last value will be m asterisk 32 minus 1. Right. Alright. Now, to view the upsampled signal and the original signal, we may have to again go for plotting functions. Do you want me to plot? Let me have some. Let me go to a fresh page. Subplot of 3, 1, 1. Let me take 3, 1, 2 even is sufficient. 3, 1, 3 is also okay, because in the previous case you've gone up to 3, 1, 2. So let me have 3, 1, 3. How to represent it? Now let me take the signal stem of yes, m minus 1 colon m. Agreed. Yeah, because we just take only the signal under consideration. M asterisk 32 minus 1 is the maximum scale without which we cannot work. And I just take interpolation output from where? M minus 1 asterisk, sorry, m minus 1 colon colon. What is it? Guess and tell me. Yes, the last segment may be defined as m asterisk 32 minus 1. Okay, we shall also work with uh, sampling rate conversion by I by D, but let's first of all start with the program. Clear all, close all, CLC. Let me define the time scale. N is equal to 0 colon 1 5. Maybe the time maximum limit will be 15 in this case. Good. And L is equal to 4, and M is equal to, or let me say, uh, what is M? I. Let me call I is equal to 3. Okay. I is equal to 3. I is equal to 3. Right? L can even be replaced by D by I. Okay. Except I by D or D by I. You can just go for or I by D, whatever it may be. let's see how does it work. How does it work? Let me generate an input signal. The signal is x is equal to cos of, right? Cos of 0.2 asterisk pii. Yes, 0.2 asterisk pi en. Original signal is ready. Let me have an upsampled version. V1 is equal to, let me have the version will be upsampling operation. Upsampling of the input, comma, upsampling is to be given by, for example, even if I change the values, I think you won't mind. Let me have the decimation factor as 3 and interpolation factor as 4. So let me have x comma I. The signal is upsampled. Okay. Let me also have y1, which is actually the output of a downsampler. What is applied as an input to the downsampler? Let me apply v1. What is the amount of times it has to work with decimation? Right? Sorry. What is it? Interpolation. Because the previous case we worked with interpolation. So let me have the decimation work here. V comma D will be ready. And upsampling is carried out, downsampling is also carried out. Let me define two lengths scale. R is equal to 0 colon length of, yes, length of V1 minus 1. Similarly, let me have M is equal to 0 colon length of, what is the second part? Y1 minus 1. Let me plot the values. How to plot it? Sum of n, stem of n comma x, stem of n comma x. What is the second one? Let me plot the stem of r comma v1. Yes. Similarly, let me plot the stem of, that's why I said it is necessary to prepare r, m, n, three different time accesses have been defined. One is, you can see the program. One is n is equal to 0 colon 1 5. The second one is r, 0 colon length of v1 minus 1. M is equal to 0 colon length of y1 minus 1. So let me plot. The first plot is over n comma x. Second plot is r comma v1. The third plot will be, what is the third plot? It is actually m comma, yes, y1. Y1. I just want to show you the effects of consecutive time sampling and upsampling. Is that clear to you? I think I have to introduce the operation. V2 is equal to downsample of, what is the downsampling input signal? X comma m. Good. Downsampling is carried out. What is the second one? R is actually is defined with initial values equal to 0 and length of V2 minus 1. Length of V2 minus 1. Good. Y2, what is Y2? Y2 is equal to upsample of V2 minus L. Upsample of, what is the upsampling operation? For example, input is V2. Let me upsample it. What is the factor with which it has to upsample? EL. Okay. Upsampling is over. we shall define small m whose lower limit is 0, upper limit is length of v2 minus or length of v2 comma l. There comes a question whether v2 we have to use or y2 we have to use. It's necessary that the output signal will be of y2 most probably. So let me plot the length of the signal up to that one, v2 comma l. Okay, m is ready, y2 is ready, n comma x is ready. So let's plan. Thank you.